So after doing some reading and looking at this example that we created in the last video, I've realized what I've done here is massive overkill for what this actually needed to be. And so I thought we'd address that. And the first thing I want to do is completely comment out all this logic that we built originally. And I'll explain why we're doing this in a second. So the always block is meant to deal with clock edges. So, positive going, negative going. In this case, this is just a simple logic function. There's an output based on, in this case, inputs. Simply, there's no clock edges or anything like that to drive it. So we don't need an always block. This doesn't need to look for edges on these. It just simply needs to monitor the inputs and then drive the output. So we should be able to take each one of these logic blocks and simply copy them up as I'm doing here. Oh, missed the semicolon. And this guy. So what we've done is we've transferred, in this case, the XOR function is sitting right here. And remember that because the LEDs require a low output to turn on, we've got the not symbol here. So we do our XOR, and if the XOR output's a 1, these conditions are met, we not that over to a 0 so that the LED turns on. So for the first 3 of these, that logic is sound. But if you remember in the little design we did before, because this is implements a not and or a NAND function, we went ahead and inverted in here so that the output of this was a true NAND output. And then, of course, I inverted all of these so that it became, if the condition was true, it would not turn the LED on. Because there's technically a double not here and here, those 2 knots really aren't needed. It was done just to keep this consistent, this to be a true NAND function. Up here, we really don't need the not here on the NAND function. Because the output of the AND function here is knotted, this works as is. If both inputs are 1s, the output is low. And the output being low, of course, turns the LED on. And what we want to demonstrate is that both inputs are 1s. Of course, now I'm saying this and I'm rethinking what I'm saying, as I always do, because I hadn't thought this fully through. So the NAND function has a 1 on the output. I do need to invert this still. So the NAND function, if both inputs are 0, the output is a 1. And on the case of a 1 output, we want the LED lit. If either 1 is a 1, the output goes low. Oh boy, am I getting this wrong? So if both inputs are 1s, the output is a 0. In any other condition, 0, 1, 1, 0, 0, 0, the output is high. This can't be correct because it's the same as our AND function up here, which is sitting. No, it has to be inverted this way. Anyhow, sorry for the confusion here. It's early. I haven't really finished my first cup of coffee yet. But this should re-implement this without needing to look for edges, because we don't care about edges. This is just, there's 2 inputs in each one of these cases and it produces an output. There's no edges to synchronize to or trigger something on, etc. So this greatly simplifies the code. My assumption at this point is this will compile. Let's go ahead and see if it'll compile. It should. Yeah, that inverting the output to turn the LED on is confusing. Anyhow, the compile was successful. We should then be able to program the device. Which has happened. I'm debating, yeah, let me go ahead and break the other camera out. So the board has been programmed here with our changes. And what we should see here is we do an XOR on these first two. So if either input, so XOR is right now we have a 1 1 in, so we get a 0 out. We have a 0 1 in, so we get a 1 out. A 1 0 in, so we get a 0 out. And if they're both low. Now this is interesting. No, I'm seeing an artifact on the camera here. I thought there was an issue, but there's not. So the XOR is working. I believe this was the and. Let me go back and look at the source really quick. Yeah, so these two here are the and. So right now with the switches on, not pressed, there's a 1 1 in, so the output's a 1. If either input goes low, or both inputs go low, we see the output go low, and then we have the OR function on these two switches. And right now both inputs are a 1, so the output should be a 1. If either input is changed to a 0, it stays a 1, but if they're both taken to 0, there it is. With them both 0, the output goes low, so that is producing an OR function. And then we have the not AND up here. So the final two switches are both open, so the inputs are 1. And with both inputs being a 1, the AND part outputs a 1, and then it gets knotted to a 0. If either input goes low, the output of course becomes a 1. And if both of them are low, obviously the output becomes a 1. So this shows that that major simplification I did actually appears to work fine. It should. These are just basically implementing 4 standard logic gates at this point. So anyhow, as I learn Verilog, hopefully you're, if you're trying to understand it along with me, that this was useful. I apologize for the misleading you in the previous video. So just a quick recap and to end the video here. We'll look this over one more time. We've implemented our 4 logic functions simply in a single line statement here. These inputs are being monitored and the output being set accordingly. There was no reason to have clocks on this edge detection. It just was overkill. I'm not 100% convinced that block even did what I thought it did. Just apologize quick for the previous video. Again, I think seeing the process I go through as I learn might be useful to some. I'm guessing some viewers caught this and went, hey, what are you doing? Anyhow, I'll wrap this up here and get this mixed and loaded, and we'll move on to the next video shortly. Bye.